Welcome back to the module Robot Statics. So in the last class you saw a link with forces and moments, and we could deduce the torque at the joint through its own weight. Today we will see what a gravity compensation is, why is it required, what are its application. We'll also see the external forces and torques, how they can be taken care of in control algorithms while designing the robot and while applying a robot for a particular task. So let us begin with today's lecture. So yes, what is gravity compensation? It is actually a minimum amount of joint torque and force that the joint actuator should provide even when the robot is stationary. What does it mean actually? Let us say your robot is stationary at a point. Even to remain there without even trying to move or do any task, so it needs some minimum amount of torque at its joint. Got it? So to stay there due to gravity, there is some amount of torque that comes due to the link masses. Okay, link masses, and the links are connected in series. Why they need to be analyzed so carefully? Because it is a three-dimensional structure. So each and every link is now oriented in space anyway, like it is not necessarily in a plane. So it is not so trivial to calculate the joint torques. So we'll do using our vector matrix approach to do that. So that is what we'll be doing today in gravity compensation. So application, what we see modern robotics, you see there are cobots. There are collaborative robots that work in close collaboration with humans, and they sometimes don't even have joint brakes to hold the robot in case it fails. And most of the time they work in impedance control of thing, in which it is not under a position control system where you have a brake, you have a single input single output system. When you have controllers that run the joints only in position control mode, rather it is controlling in terms of joint torques. Okay, so that is how it runs. So it needs a close attention to the torques that is arising due to the gravity part of it. So lead through programming, that is a cobot. So I'll show you a quick video that I have recorded earlier in my lab. So you see what I am trying to do. It's a freely floating robot, okay, that floats in the air, okay, because it is gravity compensated. So I don't feel the masses of the link when I am able to manipulate the robot using my hand. Okay, I am taking it to different location on the path which I am trying to follow. Okay, so this is a lead through programming, when I can drag the robot to the desired location, teach those points, and a robot will in turn record those and repeat that. Okay, so this manual teaching process is possible because the robot is totally gravity compensated. The robot controller doesn't feel as if there is any mass of the links. It is as if it is in space. Okay, if you take this robot in space and there is no gravity, so there is no influence of gravity on the links, and finally it sees no torque at all. So if you move the robot, it only requires the torque which is required to dynamically move the robot. So all static torques are absent. Okay, so this is how one can teach a modern robot, and you see now it will repeat the sequence which is taught. So repeating is something else, but while teaching I could drag the robot. That is what is an application of gravity compensation. So this is a type of collaborative robot, that is KUKA IVA you call it. It's a 5 kg payload capacity. Nowadays even greater payload capacity like 20-25 kg payload capacity cobots are also there, which can also be dragged in a similar way. You see? So this is one of the application, and controller implementation with floating robot model is more easy. You see, a robot should behave in a similar manner irrespective of the direction. So if there is no gravity from one side of it, so all the directions, it becomes similar for the robot controller. So designing a controller is much more easier if you make your robot gravity compensated. That means your idle torque of the robot is just taking care enough, it is providing enough torque that is to take care of the torque that is coming due to the gravity. So finally it is making your system freely floating in air. Okay, so uniform behavior in all the directions can be achieved. So what are the prerequisites for this type of control is, you have identified your robot. Why do you need identification? Because robot link, although it appears like a solid body from outside, it is very complex inside. There are transmission system inside, there is motor, there is a reducer, there is electronics, there are wires which are hanging all around. So yes, inside it is very, very complex. So even with almost like complete information available through the CAD model of it, but still it requires to be identified, because inside it is very complex, which cannot be estimated before assembling this link. So once it is assembled, it needs to be identified. You do some kind of experiments to find out the center of gravity location and the total mass of that body, that is the link. Okay, so accurate CG location with respect to the link is to be known, and its mass is to be found out by experiments. So finally, that is the prerequisite before we proceed further with gravity compensation or the analysis of gravity compensation. So that is obtained through precise CAD models and through identification experiments, as I have said, with isolated link and or after assembling the link to the robot. So even after assembling it to the robot, there are experiments to find it out, because these robots normally they have torque sensor inbuilt to the robot joints. Okay, so that is what it helps to do those kind of experiments. So let us just quickly get into the gravity compensation. Okay, so static joint forces and torques due to the gravity. So before we begin, we'll just look at forward kinematic transformation matrix, what it says. So forward kinematic transformation matrix is formed like this. So you see you have Ti in frame 1. So forward kinematic transformation matrix is always with respect to the ground frame, which is attached to the base of the robot, that is frame 1, which is here. So this is the transformation matrix. What does it contain? Basically, let us say you are talking about this ith link. So Qi will denote the orientation of the ith frame which is attached here. Okay, frame which is attached here. So it is basically A1, A2, that is the link transformation matrices. So it is a product of all of them, A2, A3 and so on so forth till An. So it gives you the orientation of the link frame which is attached here. So that is what is Qi, that is 3 cross 3 matrix, and also the position of this. So link orientation is given by the matrix which is here, and final position it gives, it is this one. So OI plus 1, it is the tip of the link, that where your link ends. So this is the frame which is attached at the end of your link. If you can recall the DH parameters, how we placed all the link frames, so you remember this is the frame which we place at the end of the link, that gives you the position of OI plus 1, that is the origin I plus 1. So that is the point about which link I plus 1 rotates or translates. It depends on what type of joint it is. So that is your OI plus 1. So this is what is your transformation matrix. Moving ahead, the position vector of the center of gravity, that is this location, that is equal to Cix, Ciy, Ciz. I represents the link number. So it is transposed because I have written it in horizontal fashion, row wise. So it is transport. So it is effectively Cix, Ciy, Ciz. So in column format with respect to the base frame O1 which is here. So it may be given as Ci is equal to Oi is this, plus Di. Di is the location of center of gravity with respect to its own frame. So normally this is known. If you have a fixed shape link, So normally the center of gravity is well known with respect to the frame, any of the frame which is attached to it. So you can calculate the center of gravity location with respect to the joint also. That is quite easy. So that is what is di. So but this is in frame OI. Okay. So in order to know and create this vector triangle, so all the triangle vectors should be in the same frame. So I prefer it putting it in the frame 1. So I have multiplied di to qi, that is in frame 1. So qi is nothing but, as I said, it is link transformation matrices, product of all of them till here. So that is what is qi. So it gives you the orientation of y frame with respect to the one frame. Okay. So di is now transferred to the frame 1. So now this di is in frame 1, oi is this one, and ci is the vector which is here. So this is this vector. Got it? So that is giving you the location of center of gravity of ith link with first frame, which is here. Okay. So now any intermediate vectors dik, what are they? That is dii, dii plus 1, so din. So any I kth link will come here, so it will be dik. So k varies from I to I plus 1, I plus 2, finally till n. So di's are all the vectors which are originating from ith joint. So it is all of these. Got it? So why I am considering this? Because I know, so whatever are the links that comes after the ith joint. So after this joint, if I am calculating torque at this joint, okay, so all the links that comes after this joint, this one, all the links that will come after this joint will have its influence on the torque, final torque, or the moment that is received here. Got it? So that is the reason I am calculating all the vector distances, so that I can take the product, cross product with the gravity forces for all the links. Got it? So that is what I am going to do. So this is the reason I am calculating all these vectors. Got it? Moving ahead, so moment due to gravity at the ith joint. Okay, ith joint will be the result of moments due to all the links that comes after OI. All the links after OI. Okay, so now I will be using dii, dii plus 1, di, and so it is sum of the products of all the dik cross mig, so sum of all those. So your k varies from I plus 1 up till n. So you got it? So it is taking sum of all those. So that is what is this. So ni is nothing but the moment which is there. So ni is the moment which is realized at this joint. Got it? So this is how it is calculated. So I now know the total moment that is coming over here. So net torque due to gravity at joint I, if you know the moment, you have to project this moment along the axis which is here. So you know already that this is nothing but your zi axis, and that can be extracted out of forward kinematic transformation matrix, that is till here. So it is product of all the matrices till this location. So that is what will quickly give you the orientation qi as well as the vector oi. So both of these are combined together, and that is there in your transformation matrix which is here. And you know very well that this gives you the position, this 3 cross 3 gives you the orientation, this is 0 0 0 1. So the last column of this orientation matrix 3 cross 1 is your EI vector. So that is this vector, and that is what is aligned along ZI. So if you take dot product, that is, if you want to project your moment along that direction, you have to take dot product with that unit vector. So EI is an unit vector along ZI axis. So taking dot product gives me the torque at joint I. So that is what is required. So you now know at ith joint it is this torque which is going to come. So all the links are connected with joints. All the joints will have its own torque, and they will have a similar summation of all the cross products which are there. And you have to take dot product to align it along the joint axes to see all the torques. Okay, so first link, you know, it is always aligned like this. It is 0, 0, 1. So it is 0, 0, 1. It is aligned with the first perpendicular to the surface plane, that is EI. So first frame lies at the fixed base and ZI is along this. So it is given by 0, 0, 1. Others can be calculated using transformation matrices. Got it? So this is your torque. So finally the net gravity compensation torque vector, it is aligned, it is all the torques are here. So you can just put it in array fashion or in column vector format. So it is tau 1, tau 2, tau 3, tau 4, tau 5 and till tau 6 if it is the 6 degrees of freedom robot. So this is what is the set of torques that is to be fed to the robot all the time to maintain its position even if it is not moving. So it has to balance against the gravity and no brakes are applied. Got it? So this makes your robot freely floating. Now you will feel as if there is no gravity which is acting. So all the time, but this is dynamic in nature, you know, because if you change the orientation or position of your robot, so joint angle changes. That finally changes all these vectors. So dynamic changes do happen to these, and finally your torque will also change. So every position will have a different set of torques that is to be fed to all the joints. So that is to be updated every time. So you need to continuously take the feedback of joint angles, update your matrices and vectors, and update the new joint torques which is to be fed to the robot. So that is how it is made dynamically stable. So any position, if you take it, it is stable. Okay, it will not move due to the gravity. Got it? So that is what is gravity compensation. Okay, so now let us move to the second topic of today. So this is resolving external force and torque to joint force and torque. Why this is important, I'll tell you. Again, your robot has to encounter and do some sort of task. So there are many tasks which requires end effector of the robot to be in contact with the environment. Okay, so if it makes contact over here at the tip of your robot, okay, so this reaction force that is here will create some torque at each of the joints. So there is a torque which is realized here, over here, okay, over here. So all the joint will see some sort of torque that comes due to the force that acts at the end effector. So this is the minimum amount of torque which is now required to take care of the forces. Okay, so in order to maintain your position even with that force, you need this additional amount of torque. So apart from the gravity torque, you now need this additional torque at the joint to face that forces or to generate that kind of force. Okay, so that is what is the task. So what are the applications? Let's say collaborative manipulation. When one of the robot is holding something, another robot is trying to maneuver it. So it may be a master-slave kind of robot. That kind of collaborative manipulation is there. Then the robot which is master will move the robot in position control mode. Whereas the other one which is holding it, it has to feel the forces. Okay, it has to feel the forces that comes at its end. Okay, and as soon as it feels the force, it has to generate equivalent amount of torque so that it can maintain the constant force, and it can, if required, it can move along with the master robot. So that kind of robot collaboration can be achieved. Human robot interaction, let's say you want to again move your robot based on the external force. I'll show you one small demonstration over here. So you see, what I am trying to do here is I am trying to move this robot using the forces that I am applying from the tip of the robot, that is I am applying at the end effector. So I am applying a kind of push pull, different sort of direction, force direction. Okay, so there is a force sensor that is feeling the force, and it is converting those forces to the equivalent amount of joint torques by kind of limiting over here, because this is industrial robot. This doesn't allow you running the robot in torque mode. So here I am just limiting the forces which are there at the joints, force and the torque which are there at the joint. See it once again. So yes, so this is what I meant. So it has to take care of the external force. So this is an example of human robot interaction. Handling tasks in contact, it is a continuous control. Let's say you want to do a grinding task, grinding, polishing, buffing. So all those tasks require your robot to maintain a constant force against the surface which it is polishing, grinding, buffing. So whatever task it is doing, so constant force requirement is there because you want to grind it uniformly all over the surface. So wherever your robot goes on the surface, you have to maintain the same constant forces against the surface. Okay, so in order to do that, you have to have a constant changing torques at the joint. So those torque will now produce, all the joint torque will now produce the end effector force which it is trying to maintain. So this is an additional torque. So there are many contributions of torque. First contribution is due to the gravity torque. You have to compensate against the gravity. So that torque is fed to the robot so that it can maintain against the gravity. Second one is to do some kind of job, that is to take care of the external forces. So this is the one which is external force. There are many other torques which are there. One of them may be to move the robot in space with certain velocity and acceleration. Okay, so those are the different kinds of torque which are contributing to the total torque which the actuator is generating to do a whole amount of task which a robot normally does. So handling tasks in contact, that is a continuous control is done. So surface finishing task, robot assisted assembly, that is again a continuous task that a robot can do. So all the time it may be driven by some sort of external constraints also. You may require to generate some force in one direction, some other force in other direction. So that kind of controllers are also there. So that is also requiring external forces and torque that has to be resolved to the joint torques. So pick and place, that is a discrete static load that comes on the robot, and your robot has to take care of that. So design any sort of controller for all these applications. So it requires explicitly stating your joint forces and torques for any external forces and torque that comes at this location. That is the tip of your robot's end effector. Okay, so this is a set of application. This is not an exhaustive list. There are many others also. So let us quickly analyze this kind of forces and torques. Okay, so yes, using the principle of virtual work, that is an quite old stuff in engineering mechanics that you probably have done it quite number of times. Now we are applying the same thing to the robot also. So let me just introduce you to the terms which are here. So if this tip of the robot moves by a small linear and angular displacement given by delta x, which is here. Okay, so if this moves by that small amount of delta x at the tip, okay, so this must be doing some kind of work. So this delta x into the wrench. What is this wrench? Wrench is a vector that contains moment and force. Okay, so that is your wrench. Wrench is given by 3 cross 1 moment, 3 cross 1 force, so it is total 6 cross 1 vector, so that is your wrench vector. So wrench multiplied by the angular displacement and linear displacement. So effectively moment is multiplied with the angular displacement and forces are multiplied with the linear displacement if you do this. So input is this one. So that is what which goes at the end effector level. So that is the output work which is done by the robot. Okay, so it is wrench into the displacement vector. So that is there. And the second part is the input work done by the joint. So it is nothing but this is your array of torque which is there at each joint. So that is tau 1, tau 2, tau 3, tau 4, tau 5 and tau 6. So it is all the 6 joints torques which is here for a 6 degree of freedom robot. Definitely it will be different for a 7 degrees of freedom robot. So torque transpose, because it is to be oriented like this. So you have tau 1, you have tau 2, you have tau like this arranged over here, and you have joint angles which are here. So torque into joint angles which each of the joint is moving in order to give you the displacement delta x. So that is your input work done. So input work done is equal to output work done. So it is a small incremental displacement which is written here. If you remember your virtual work principle, so it is to be taken like this. So I have just balanced both of them. So now this is your final equation which says your output work done and this is your input work done. Torque into displacement, angular displacement of the joint. It can even be a linear displacement if it is a prismatic joint, whereas this one is your output work done. So wrench into the angular and linear displacement array that is over here, that is delta x. Got it? So now I am replacing delta x by Jacobian of delta theta. So if you remember, your Jacobian relates the joint rates to the end effector rates using this relation. It is a small differential that is here. So I am quickly substituting this to this equation. So what I get here is wrench transpose. Instead of delta x, I will put j delta theta over here. Okay, and right side remains as it is. So you can write it finally like this. So wrench transpose Jacobian is equal to torque transpose. This is torque at the joint transpose. Okay, taking transpose both the sides, I can write it like this. So it becomes torque is equal to Jacobian transpose of external forces. So that is the wrench that comes over here. So whatever is the external force and torque that you want to maintain over here, in order to maintain that, you have to provide this much of torque at the joints. So it can be otherwise also. If you are providing this much of torque, okay, so you will see this amount of force at the tip of your end effector. So this is how it is related, and this is very, very important in order to design any controller, for any impedance controller, stiffness controller, admittance controller, or any kind of controller to do any specific kind of task. Okay, so that's all for today. I think that should be enough for robot statics. There are many other parameters also that can be studied, but we'll limit over here because industrial robot, you don't have much freedom to handle much of the things. So this should be quite good enough to understand the kind of application normally which industrial robot are made for. Okay, so we'll end it here. So in the next class, I'll do kinetostatic measures for robot design, in which we'll be doing velocity and force ellipsoids. Okay, so that's all. Thanks a lot.